Hello everyone, my name is Emma Spors and I'm a senior mathematics and data science double major. After graduating this May, I will be returning to SDSU next fall to complete a master's in statistics. Today I will be talking a little bit about fractals. This is an interesting topic for me because it was the first advanced math concept I had ever learned. I was introduced to fractals in the honors colloquium, Mathematics and the Arts, the spring of my freshman year. That class was one of the main reasons why I chose to switch my major to mathematics. So I think that it's very fitting to round out my undergraduate degree with this topic. So, without further ado, let's explore the world of fractals. Fractals are shapes that are beautifully simple, yet infinitely complex. They have existed in artwork, architecture, and mathematics for centuries. However, it wasn't until the last 70 years that mathematicians and scientists have expounded upon these ideas to cultivate this new area of mathematics. In the broadest sense, fractals refer to complex repeating patterns, and across many different disciplines, including physics, chemistry, biology, physiology, geology, and economics, experts have identified the telltale signs of fractals. So, in addition to being mathematically interesting, experts have been able to apply their knowledge about fractals in an attempt to better understand the world. In order for us to gain insight into the world of fractals, we will first begin with an overview of their history. Then I will describe some of the major types of fractals, followed by some specific examples, including properties of the Koch snowflake and the Mandelbrot set. In addition, I will introduce the fractal dimension by way of the similarity dimension, followed by a short discussion on the applications of fractals. As I previously mentioned, fractals have existed for centuries. However, it wasn't until 1972 when Carl Weierstrass produced a function that was everywhere continuous but nowhere differentiable that we saw one of the first true fractals. The graph of the function, seen on the screen, exhibits self-similarity. Self-similarity implies that magnification on part of the object results in an image that looks like the whole object. Later, in 1883, Georg Cantor introduced examples of the real line known as the Cantor sets, which are again considered to be a fractal. Then, in 1904, Helge von Koch gave a geometrical definition of a self-similar shape and produced a hand drawing of what is now known as the Koch snowflake. Wacław Sierpiński produced the Sierpiński triangle and the Sierpiński carpet around 1915. Their Sierpiński triangle is pictured on the screen. In 1918, Felix Hausdorff expanded the definition of dimension, which allowed for sets to have non-integer dimensions. This idea will become important when we discuss the fractal dimension later on. Up until this point, mathematicians were computing and drawing everything by hand. In addition, all of these shapes were not even called fractals yet. It was the advent of the computers in the late 1900s that allowed fractals to be propelled into more practical use. In fact, Benoit B. Mandelbrot had been working at IBM when he first began his work on fractals. He began by writing about self-similarity and measuring coastlines when he began to become inspired by the art of roughness. This led him to coin the term fractal from the Latin word fractus, meaning fractioned or broken. He went on to unify the study of fractals and even made his famous self-titled set and fractal, the Mandelbrot set. He's considered to be the father of fractals. Previously mentioned, the term fractal refers to a wide variety of shapes. However, they can generally be classified into three types. First, we see self-similar fractals. These fractals exhibit scale invariance, where magnification on part of the object looks exactly like the whole. We see these in fractals such as the Sierpinski triangle and Koch curve. Quasi-self-similar fractals can appear slightly different upon different magnifications, but they generally hold their shape throughout. We see these in shapes such as the Julia sets and the Mandelbrot set. Both of these fractals, the self-similar fractal and the quasi-self-similar fractal, are typically mathematically derived. The statistically self-similar fractal, in contrast, are what we often see in the real world. These shapes have proportions that can be considered to be reduced scale representations of the whole object. Examples include sea coastlines and pulmonary vessels and lungs. I've also included pictures of other natural fractals. From left to right, this includes Romanesco broccoli, a snowflake, a fern leaf, a river delta, and a tree. Now we will see some of the interesting properties of fractals. The Koch snowflake is a great example of this. The picture on the right shows how the Koch snowflake is produced. You begin with the equilateral triangle and then remove the inner third of each side and add a new, smaller equilateral triangle facing outward with its base removed. This constitutes a single iteration. This process is repeated infinitely and creates a shape that looks sort of like a snowflake, hence its name. In addition, the result produces something that has an infinite perimeter but a finite area. The following two theorems will prove these ideas. First, we will show that the perimeter of the Koch snowflake is infinite. Like I mentioned before, the Koch snowflake begins with an equilateral triangle, and we will denote its side length with S. To find the perimeter of the Koch snowflake, we need, at an iteration n, we need to define the number of sides and their length at iteration n. Therefore, we will let n sub n be the number of sides at iteration n. We know that at n sub 0 there are 3, and for each iteration there will be 4 times the number of sides from the previous iteration. We can see that this is true because for every one side at the current iteration, there are 4 sides in the next. The length of the sides at iteration n are 1/3 the length of the sides from the previous. Thus, to find the perimeter P sub n at iteration n, we take the number of sides times their length. Because new triangles are added infinitely, the perimeter of the Koch snowflake is found by taking the limit of P sub n as n goes to infinity. Because 4/3 is greater than 1, the limit as n goes to infinity of 4/3 to the n is infinity. Therefore, we see that the perimeter of the Koch snowflake is infinite. In contrast, we will show that the area of the Koch snowflake is finite. Again, we will begin with an equilateral triangle of side length S. To find the area, we will need to know the area of the original triangle, the number of new triangles added, and the area of each of those new triangles. So first, we will define the number of new triangles at iteration n. This is equivalent to the number of sides from the previous iteration. This is because we add a new triangle to each of the sides from the previous iteration. The area of each of these newly added triangles can be found by taking 1/9 the area of the previously added triangles. Thus, we can find the total new area added in iteration n by taking the number of triangles times their area. The total area at iteration n, a sub n, can be found by adding the area of the starting triangle to the sum of all the areas from the added triangles through iteration n. This is done by a summation. And by using collapsing geometric sums, we are able to get the right-hand side of the equation. Again, since new triangles are added an infinite number of times, we take the limit of a sub n as n approaches infinity to get the area of the Koch snowflake. Since 4/9 is less than 1, the limit as n approaches infinity of 4/9 to the n is 0. Therefore, we see that the area of the Koch snowflake is 8/5 times the area of the original triangle. From these two theorems, we see that the Koch snowflake has a perimeter that extends in an infinite length, but is scrunched into a finite area. Next, we will take a look at the Mandelbrot set. The Mandelbrot set is perhaps one of the most iconic fractals, and it's not hard to see why. The video on the right-hand side shows the magnification upon the boundary of the Mandelbrot set. It really shows the beauty and complexity that exists along its edge. It is quite mesmerizing to watch, and you can find plenty of videos on YouTube if you would like to check it out more. The Mandelbrot set M is the set of complex numbers C that remain bounded under the quadratic recursion equation listed on the screen. For example, we can see that 2 is not in the Mandelbrot set. Upon successive iterations of the equation, the values increase indefinitely towards infinity. Therefore, for 2, the quadratic recursion equation is not bounded. In contrast, I is in the Mandelbrot set. Upon successive iterations, the values in the equation remain bounded between -1 plus I and -I. Thus, we see that I is in the Mandelbrot set. From the definition, the Mandelbrot set has some of the following properties. This theorem helps us decide what is in the Mandelbrot set and what is not. First, we know that M contains all complex numbers such that the distance of C from the origin, or the magnitude of C, is less than or equal to 1/4. In addition, if C is in M, then the magnitude of C is less than or equal to 2. Or, if the magnitude of C is greater than 2, then C is not in M. This may be a bit confusing at first because these conditions seem to be saying the same thing with different numbers. The picture in the upper right-hand corner helps explain the motivation behind this theorem. Everything that is shaded black is included in the Mandelbrot set. And while it's a bit hard to see from this picture, there is an arm of the Mandelbrot set that does extend all the way to -2 along the x-axis. The smaller circle has a radius of 1/4. As you can see, everything inside the circle is contained in M. The larger circle has a radius of 2. All the values that are in the Mandelbrot set are contained within the circle. However, there are some values that are not in the Mandelbrot set that are also in this circle. Thus, we can see point 2 means that the magnitude of C being less than or equal to 2 is a necessary but not sufficient condition for C to be an M. In addition, the fractal dimension of the boundary, or the edge of the shape, was proven to be 2 by Michiro Shishikura, a Japanese mathematician. This proof is quite long and technical, so it will not be discussed at this time. But what is the fractal dimension? Also known as the Hausdorff dimension, the fractal dimension allows us to quantify all the different shapes that could be considered as fractals. While often not an integer, but sometimes it can be, the fractal dimension allows us to measure the complexity or roughness of a pattern. There are several different ways to calculate the fractal dimension, but we will focus on the similarity dimension. Still, before we can get to that, we need to understand traditional dimension in terms of scaling. While linear algebra holds the more rigorous definitions of dimension, for our purposes, we will consider dimension with scaling. If we consider a one-dimensional line, a two-dimensional square, and a three-dimensional cube, we can see how the dimension plays out. If we were to scale the line by 1/2, it would take 2 of the new miniatures to rebuild the original. A square scaled by 1/2 would require 4 of the new squares to rebuild the original. And a cube scaled by 1/2 would require 8 of the new miniatures to rebuild the original. The values, the number of miniatures required for different dimensions and scaling factors can be found in the table on the right, with the scaling factor along the left, dimension along the top, and the miniatures needed in the middle. These patterns can be summed up in the following equations, where M is the number of miniatures required to rebuild the original, C is the scaling factor, and D is the dimension. We can extend this idea of using scaling and dimension to self-similar fractals. We see that if the Sierpinski triangle is scaled by 1/2, it would require 3 of these new miniature shapes to reconstruct the original. Thus, by using equation 2 from the previous slide, we see that the dimension is about 1.585. But what does this mean? We can interpret this as the Sierpinski triangle existing somewhere between the first and second dimension. It has more mass than a line shaped as a triangle, but less mass than a two-dimensional triangle of the same size. Before we can discuss the fractal dimension for self-similar fractals, we need to understand the self-similarity constant. This is an associated value between 0 and 1 that self-similar fractals have. While it does have a mathematical definition, it can easily be found by observing the fractal image. The self-similarity constant refers to the fractional scale at which a piece of the fractal looks exactly like the whole object. For the Sierpinski triangle, we see that a reduced scale version of the triangle is 1/2 the length of the side. Therefore, S equals 1/2. For the Cantor sets, a reduced version is 1/3 the length of the whole object. Thus, the self-similarity constant is 1/3. In addition, for the Koch curve, which is a section of the Koch snowflake, a reduced scale copy is 1/3 the length of the whole object, making S equal 1/3. Similarity dimension is one of the ways that we can measure the fractal dimension of self-similar fractals. Self-similar fractals can only be scaled by an exponentiation of their self-similarity constant. Thus, we can edit equations 1 and 2 from the traditional dimension slide to reflect this constraint. Thus, we have the similarity dimension of a self-similar fractal f as the natural log of the miniatures needed over the natural log of 1 divided by the self-similarity constant. Additional examples of the similarity dimension include about 1.26 for the Koch curve, about 0.63 for the Cantor set, and about 1.89 for the Sierpinski carpet. So what are the next steps? Unfortunately, we cannot use the similarity dimension to find the fractal dimension of shapes that are not self-similar. So, for more practical purposes, we need to define the box dimension. This is how we find the dimensions of irregular fractals, such as the coastline of Britain, which has a fractal dimension of about 1.15. For timing purposes, I will not be going over the details of this, but they will be further outlined in my paper. Understanding the box dimension, we can use fractals in a variety of applications. As previously mentioned, the box dimension has been used to measure the roughness of coastlines. However, what I find particularly interesting is their use in human physiology. Scientists have used the fractal dimension to detect changes in the white matter of brains due to neurological disorders such as Alzheimer's and ADHD. In addition, the fractal dimension has been used to map lung structures and identify and understand cancerous tumors. Most recently, experts have been experimenting with monitoring COVID-19 trend lines with the fractal dimension. So, just like the world of fractals, the applications of fractals are endless. Today, we have just scratched the surface of the world of fractals by discussing their history, types of fractals, famous fractals including the Koch snowflake in the Mandelbrot set, as well as looking into the fractal dimension. Like their infinite nature, fractals provide an infinite area of study. So, while we focused on fractals that could be represented as on a two-dimensional surface, additional learning could be completed on fractals that exist in higher dimensions, such as the Menger sponge. Fractals also have a very strong connection to chaos theory, which would provide enough information to keep anyone busy for a while. And this is on top of all the other applications fractals have in real life. Ultimately, though, I hope that I was able to share with you some of the beauty and intrigue behind the world of fractals. Thank you for taking the time to listen to my presentation and letting me share what I have learned with you. In addition, a big thank you to Dr. Flint for advising me on this project. Her knowledge and feedback was an integral part of my learning throughout this semester.